Let me introduce our next speaker. His name is Arafat. He came from India, and he's going to talk about visualization in Go. Let's start.
Hi everyone. Really nice to meet you guys. I am Arafat, and thank you so much for coming here. I came a long way to get here, so it's really, really nice to see all of you here. And thanks to the organizers, you guys did a great job. So a little bit about me. I am a programmer. I love writing code, distributed systems, machine learning, AI, all these things. I love them. I love all of it. I love hiking. Aside from programming, I like other things in life too. So I love hiking. This is one of the shots that I took at British Columbia in Canada. It's one of my favorite hikes. And I also love biking. So if you want to have interest in bikes or whatever, just let me know. This is not my shot, but whatever, I put it there. I work at Simon Fraser University in Canada, and at the university I work on very interesting problems, but unfortunately they're radically different from the talk that we're going to do today, so I can't talk about that. And pretty soon I'm going to graduate, and after I graduate, I'm going to be working at Shopify. Shopify is a really nice Canadian company, and they revolutionize how retail works and the whole retail industry works. It's like the the sibling of Amazon, except Amazon is richer and better and everything. Okay, so coming back to the talk. The talk is about visualization in Golang. And before I start this talk, I kind of want to give you a philosophical reason as to why am I doing this. So the answer is visualization gives you answers to questions that you didn't know you had. Now what do we mean by that? So before we start, I just want to ask you one simple question, just very simple question. Just let me know, how many of you have given a programming interview? Just raise your hands. Just raise your hand if you've given a programming interview. Just do like this, because that is obnoxious. So you can just do like this, and that's fine. Okay, so how many of you like giving programming interviews? Not many, I guess. But nevertheless, one thing is for sure. Programming interviews are really important, and we have to be good at them. So if you don't believe me, you can read this tweet. So basically, it's a comment from Max Howell, the author of Brew, and he said he didn't get a job at Google because he couldn't invert a binary tree. So I'm not judging anyone like Google or Max or anybody. I'm not saying that. My argument only is that if you want to get the job, you better be able to invert the binary tree. Okay. So by the way, that shouldn't be a problem for you people, because you people are generally great coders and math nerds. And my belief is that the whole traditional Russian and Belarusian education system was somehow good for mathematics and physics and things like that. So when I was a child growing up, I used to read these books. They were translated from Russian. So if anybody's read them, let me know, the original ones. And they were really amazing books, and they kind of taught me a lot about programming. So I always wanted to wonder, what would we like to read these books originally in Russian? And aside from that, I also use this website. This is probably one of my favorite algorithms website, emacs.ru. It's completely in Russian, so I read this website from Yandex Translate. It's a poor translation, so something like segmentary would be something like woodwork or something. It's funny, actually, but I still like it. So you can check it out, emacs.ru. So anyway, so now getting to the point of the whole visualizations and Golang thing. So in my head, I come from the scientific programming community, and I had this problem, which was we want to be able to visualize algorithms, data structures in Golang, and that would make it easier for us to solve problems and to understand algorithms. So I made this small library using GraphViz and Golang. So today we're going to solve a simple problem of priority queue. I'm going to solve two problems. This is the first one. So priority queue is a queue data structure with some additional properties. So normally the queue data structure is something like you put in something, and then it gets out. So it's first in, first out. So you put in 3, 4, 5, and then immediately if you take it out, it's 3, 4, 5 after that. So priority queue is different from a queue in the sense that everything you put inside the priority queue has a priority attached to itself. So let's say you put in 11, 7 to 9. You can put them inside in any order. And when you take it out, the first thing that will come out will be 11 because it has the highest priority. So the thing about priority queue is like it just you can put it anything you want inside the priority queue. When you take it out, it will always be the one with the largest priority. And now the question that comes is like, okay, we can implement priority queues really easily. All you have to do is like you make this data structure with a fixed size, with some dynamic size, and you just do, you can just write a for loop that takes out the max priority and takes out the max priority element. We can do that, but that's pretty uncool, and that's like, that's very slow if you try to do it. So instead, we're going to do binary heaps. So the thing about binary heaps is that it offers us the ability to get the maximum and the minimal element in constant time. And the insertion and deletion operations are logarithmic time. So this could let you, write theoretically a good sorting algorithm in n-log n, which is like theoretically the best possible sorting algorithm using binary heap. Now, obviously, we can do it much better and much faster than this. So we can do like Fibonacci heaps and things like that. But today, my goal is to prove a point rather than focus on the data structure itself. I want to kind of prove a point of visualizations. So we're going to learn how to, learn to love heaps. So what is a heap then? A heap is a binary tree with two special properties. It must have all its nodes. It must have all its nodes in a specific order, and its shape must be complete. What do we mean by that? What do we mean by that? So let's say this is the first property, that is the shape property. So let's say you have a binary tree, and it has to satisfy the shape property for it to be called a heap. So the shape property is that all the levels of the tree must be completely full except the last one. So if you look at the left one, so you look at A, B, C, D. So this is the last one. So the idea is A, B, and C must all be completely filled. They are completely filled, so that's satisfied. As for the D one, it may be either completely filled or it may be filled only for the left node. So in both these cases, these are acceptable binary trees. So it's kind of like this. Like if any node wants to have like a grandchildren, all the nodes of its level must have children. Basically, it's kind of like life in general. Like if you want to have grandchildren, you have to have children in the first place. Anyway. So if you look at the left one has like, if you look at the node in the B level, the left one, that has a grandchild, but the whole B level does not have children. So that's why it's not a binary heap. And this binary tree and a binary heap, and the right one, it does satisfy the shape property, so it is a heap. So okay, so we're going to focus more on this. Even if you didn't get it, it's not a big deal. The second thing is the order property, and that's the main property. So the order property basically states that when you have a heap, it must have all its children be either greater than or equal to its children. So basically, let's say if you have any node, let's say you take 1. So all its children must either be greater than the 1 or less than 1. So we're going to describe like a min heap. So basically like 2 is greater than 1, 3 is greater than 1. And let's say you take like 6. So 6 has children, 12 and 13. So 12 and 13 are greater than 6. So we kind of recursively define this idea that for any node, its children must be greater than that. So in that sense, like if you take any path from top to bottom, it will always be an increasing path. So like 1, 3, 6, 13, it's an increasing path. 1, 2, 5 to 11, that's an increasing path. So that's the second property of heap, so which is the order property. The order property helps us when we want to be able to satisfy the max heap and the min heap properties. So okay, so these are these two rules simplified. But okay, so now we understand we can look at a binary tree and we can look at that and we can go, okay, that satisfies the properties that we wanted from the tree. So, but how do we make it? Like, how do we even make the binary tree in the first place? Like, how do we make the heap in the first place? And in order to do that, you have to do it inductively. What I mean by that is, like, by default, let's say you have an individual node. Let's say you have just 71 alone. So any individual node in itself can be called as a heap. That is by default. That's like the base case. And if you add things to that base case, you can inductively build like a whole structure from that base case, and that would be the way you can inductively make a heap. So let's say in this scenario, we have like the strongly colored nodes. All these nodes are satisfying the heap property, which is like 71 is greater than 35, greater than 19, and like 19 is greater than 4 and 12. So it's satisfying the heap property. This whole part is satisfying the heap property. But we're inputting something new. We're inputting 43 into it. So now, how do we satisfy the heap property when we input something new in this? And the answer to that is, firstly, you satisfy the shape property. So you input it at the leftmost node. So that we did. We did satisfy it. We put it at the leftmost node. But then we don't satisfy the order property. So if we want to satisfy the order property, we will do bubble up operation. What we'll do is like we will look at it, and we will look at its parent, and we're going to, oh, 35 is greater than 43. So we're going to swap it, and we're going to like keep swapping it and bubbling it up until it comes at a point where it's less than its parent. So basically, we're going to put it in its place like recursively by swapping it up. So let me give you like an example. So okay, all right. So okay, so now the thing is like. How do we represent a heap? Like if we understand the heap, and if we understand the heap and its properties, how do we actually implement this in an actual like program? So we're going to implement it in a form of an array, and we're not going to like do the actual thing by itself, but we're going to take an example. So if you want to make an array out of this, you just do it like read it like this. Like this is 0, 1, 2, 3, 4, 5, 6, 7. So you read it like this, like. This is the first one, this is the second one, this is the third one, and so on and on and on. So basically, you go like level-wise, horizontally, and then you go like vertically downwards. And that way, you just describe like a heap. So enough with the talking. Like we've talked a lot about how we could describe it, how we could satisfy the properties. But let's do the main thing of the talk. So let's try to actually implement this thing, or not actually completely implement this thing, but like. Let's try to see some code and see how this goes.
Sorry, can you please do the screen?
OK, sorry. Okay. This is good?
Yeah.
All right, so cool. OK. So as I told you before, I wrote a simple library called database. So in this case, what we're doing is like on line 11, we have a tree data structure. We're defining it. That tree data structure is just an empty tree. It has nothing in it, but it has all these properties defined itself. And then we take a few sets of integers that we're going to put inside the heap. So these integers are like 41, 2, 5, 11. So you can see that there's no specific increasing or decreasing order. They could be like sometimes some series are increasing, some series are decreasing. So we have these few random integers. And we want to make a tree out of these integers. So what do? We look at the interface array, and we take a for loop through the interface array, and then we make the heap. So okay, so we can do that, but let me run this code and see how it goes. Okay, so okay, can you see it? Can you see the numbers inside it? Oh God, that's the best part. Okay. All right, so, oh God, that's appalling. But anyway, so the idea is you can define your whole tree in sort of like an array here, and you can incrementally put different integers inside the tree here. So in the for loop, like you're incrementally putting like 41, then 2, then 5. You're incrementally putting that, and you're trying to visualize these by saving it inside a file. So what the software does is that it takes any kind of data structure, and it tries to visualize it in the form of a graph. And then I've put a sleep kind of case here. The reason I'm putting it here is obviously because I want to see how the tree grows incrementally. So like, let's say if you run this code, so initially, I hope you could see something. So like there's 41, then you invert 2, then you put 5. OK, I should make it slower. This is too fast. It's too fast. What?
How do you define the count of layers? How do you define the count of layers?
Oh, no. See, the graph is automatically adjusted. I'm not defining the count of layers. It's automatically satisfying the properties. As you input more numbers, it's going to satisfy the order and the shape property. So you don't have to do it. If you have to do it, then that would be wrong. So it's actually self-adjusting graph. And by order property, let's say you have n elements. So log base 2 of n is the number of levels in the graph, obviously, right? So it's kind of like a self-adjusting. Any more questions are also welcome. So let's say this is 41. right? It's just 41 here alone. Then like you add 2 here, so like 2 goes to the top to satisfy the min heap property. Then like 5 comes here, so like 2 and 41, 5, then 2, and then this is 11. So 2, 11, 5, 41, 24. So it's automatically satisfying the whole property, and you can watch it grow incrementally. So think of yourself as a student, right? You're a student, you're trying to learn this algorithm, you find this super weird, you read these formal theories and textbooks, and you're like, this is super weird. So you use this library, you try to draw this, and then you get these, get the actual idea of how this whole thing works. And let's say if you visually understand the algorithm, so if you get a theoretical paper in the examination or something, you can solve that. But you also want to actually learn how to implement it. So in that case, you can just go through the library code, and what I've done here is I've done like push operation. So you go through the library. It's extremely well documented, surprisingly well for someone like me. But so you have a push operation. Look at this. So it's basically you have a list implementation, and you're adding it. And if you look at this bubble up thing, so let's say, so if you look at like perform the bubble up operation. So as I said before, like when I was here, I was telling you guys that. Okay. So when I was here, I was telling you guys like, let's say you have something here, it bubbles up, it goes upwards and upwards. So in that case, like if you want to understand the bubble up operation, it's basically applied on an array. So the actual implementation of the bubble up operation is like this, and it's actually really simple if you think about it. It's just comparing the index value with its parent, and it's just jumping upwards and upwards and upwards. So in that sense, we can easily define a heap and satisfy like the heap properties and understand how heap works. But this still doesn't solve our problem. Our problem was to write and implement a priority queue, and we didn't do that yet. So in order to actually write a priority queue, what we want to do is like we want to take the elements out of the heap, make it empty, and then we will have them sorted by the priority that we wanted them to be. So in order to do that, you have to do shrinking the heap operation. Now this operation is actually really complicated. I kind of planned on explaining this, but my stopwatch says that I don't have enough time for that. So I can only show you the visuals. So basically, okay, can you see? Oh, fuck. Can you see any of the numbers here? Like, can you see the numbers at the bottom? At the bottom? Okay, at least you can see the numbers at the bottom. Good thing. So what is happening here is that there was a tree upwards, and it had a few random numbers of integers. When you're shrinking the tree, you're taking the minimum number and you're putting it inside the list. Let me do it again. So like the minimum number is initially, okay. So minimum number is initially 1. See, then it takes out 3 and puts it there. It takes out 7. Oh. So it's like, I have no idea why this is happening, but so it sort of like incrementally tries to grow the tree. Like it tries to take elements out of the tree and it puts it inside the list. And you can see like how the list has sorted order. So if you look at the list, it's like 1, 3, 7, 11, 13, 16. So the list is in sorted order. So what it's doing is like it's taking out the top element of the tree and it's putting it there. So in that sense, you actually made a priority queue out of the whole thing, right? And this other visualization that you're seeing, the one at the bottom, that's also made using database. So you can actually define a list or other kinds of things in the library, and then you can understand how the algorithm actually looks like at every different step. So if you're a student, you can understand it, and I've documented it well enough that you can completely take a course out of it. So is that all we can do? Is that all we can do from the whole library? And the answer is no. We can do a lot more. This was one of the simplest examples. So this is an example. Does anybody know what the thing on the left is? Do you guys know what the left thing is? Like the data structure on the left? No, that's the one on the right. The right one is red-black tree. And that's a B tree. That's a B tree. So if you guys have used like databases like SQL or things like that, so in that you have a B tree that helps you do really fast implementations of things. So this one's like a complicated algorithm. If you've taken like an operating system course at a really good university, you might have to implement it. So yeah, so that's a B tree, and that's like a red-black tree. So you can use the library to sort of like try these algorithms out, see how they work. And the best part is like if you have your own algorithms, it's very easy to extend the library to add your own algorithms and make commits to my work. So let's conclude. So the idea basically is if you want to easily get jobs, you need to be good at interviewing. If you want to be good at interviewing, you need to learn data structures and algorithms. If you need to learn data structures and algorithms, you need to use my library. That's how I self-promote. So hashtag narcissism. But so try it out. Try out my library. It's on GitHub Arafat /database. So that's the first problem that I tried out. But this is just one aspect of all the things that I showed you. Now let's take a totally different term. Let's try to use visualizations to solve a totally different kind of problem. And we will also do that in Golang too. So obviously, another philosophical reason to why we're doing this. So here's a quote from Cole Knaflick. He's a very famous researcher. So the quote is, in school, we learn a lot about language and math. On the language side, we learn how to put words together into sentences and stories. With math, we learn how to make sense of numbers. But it's rare that these two sides are paired. No one tells us how to tell stories with numbers. This leaves us poorly prepared for an important task that is increasingly in demand. What does this mean? Basically, it means that you have this formal education of school. This is, and there's this practical life. So there's a dichotomy between, formal education and the practicality aspects, which is that you don't have to separate, English and like math and things like that. You can tell a story using data and visualizations. And in a world, if we're living in a data-driven world, the first thing that we must know is that how can we use data and make visuals to be able to make a case for any argument that we're trying to make. I'm gonna present an argument and I'm trying to make a case for it right now. So I'm going to solve a simple problem in machine learning. You guys will probably easily understand it. So the reason I'm going to do that is because I was involved with the development of TensorFlow in Golang. So it's also TensorFlow is generally in other languages, but now it's also in Golang. So when some of the really, really smart people at Google developed it, concurrently, I was developing TensorFlow for Ruby. So I'm actually a Ruby conference speaker, and I came here because it's fun. So I developed this library called Glot. Glot is a very simple kind of like scripty thing put together to make visualizations in Golang. And what it does is like it helps you make line plots, dot plots, things like that in Golang itself, because I was a bit disappointed that we didn't have that many things in Golang. So let's try to solve like a gradient descent kind of a problem. So, okay, where did we go there? Okay, so let's come back to my country. So. In India, we have this thing called land prices and area. So we have this data about my city, which is basically like you have this area in thousands of square feet, and you have the price of that place in million Indian rupees. So you want to be able to sort of make a model that helps you predict, given the area of the place in 1,000 square feet, you want to be able to predict the price of that place in million Indian rupees. So you just basically want to sort of make a model that helps you understand how this whole thing. How let's say if somebody gives you like, hey, let's say I have a plot which is of 15,000 square feet. What should I set as the price for the plot? So it could be you connect it there and it's like 15 million Indian rupees. So we sort of just want to make a simple model that helps us understand the price correlation with the area of the land. So if we wanted to do it, we could have done it like in a very theoretical fashion with like matrix algebra and differentiation. But we're not going to do it because we're not mathematicians, we're programmers. We're going to do it in an ad hoc fashion. So basically, the idea is we're going to use gradient descent right now. So gradient descent is basically a very interesting kind of an algorithm. It's kind of hard to explain. But the idea is every time you're trying to implement something in machine learning, you kind of have this cost function. Cost function is basically the error of your proposed model. So let's say you have, you defined a hypothetical solution to your problem and it has this much error. So what you do is like you look at that and you look at the error that you have right now and you just, Okay. Okay. So if you look at the error at the problem right now, you can just like took the gradient and push it downwards. So you basically adjust the variables over and over again inside the problem so that the total cost function or the error that you're experiencing in the problem goes down. So you see these small pits, and these are like the best possible solutions. So basically, just I kind of wanted to show you more, but I don't have time, unfortunately. So let's look at some code. And so let's say we define this as an initial solution of a problem. You see a line here that's this line here. So we're saying that this is initially the prediction that we have. Like if you have like 10,000 square feet, the price is 5 million. If it's 15, the price is still 5 million. So this is kind of a bad prediction for the whole data set. It's obviously not true. So we just set it hypothetically as an initial prediction, and we want to be able to improve upon this, this whole chart by running an algorithm and doing some math on it. So what we do is we define this sort of a simple function that just reads data from a file, the first step. Then it takes a few iterations. It tries to minimize the cost function. And then what it does is like it takes 1,000 iterations to do the whole thing. So in all these iterations, you're seeing this if condition here. So what this condition does is like for every 100th iteration, it stops and it prints the current status of the whole plot and the line. So let's actually run this and then see how it goes. Okay. Okay, I think. Can you see it? Yeah. Yeah. So basically, what we did was we sort of defined an initial solution. Then the solution jumped and it improved. So you can see this line. It's actually changing with every different iteration. And that's actually the improvement of the solution over different iterations. Now, it's rather unfortunate that I can't explain the whole math to you behind why this whole thing works out. It's actually pretty simple, but basically the idea is you sort of define a hypothetical initial solution, and then the solution takes a look at the data and improves upon itself. So if you look at different iterations, it slowly changes its slope. And the final solution that you get there, like the final solution that you get there after 1,000 iterations, it probably has the least of all of the cost functions in all these things. So basically what you did is you sort of incrementally defined a model and then improved it and visually showed a case for how the algorithm works. Okay, so there's a lot of math, but I had to ignore it. Sorry. And is that all? Is that all we can do from Glot? And the answer is no. We can do a lot more. We can do we can plot mathematical functions and things of that. So we can plot bar charts and lots of cool things. We can even do 3D plots with this library. And again, I didn't spend much time on the library, but I'm pretty sure it's very easy to extend it to more and more plots. So let's conclude. Let's conclude this library. So visualization is it's a really important tool in machine learning algorithms and data analysis. And combining data and its interpretations with plots and visualizations is a great way to improve your understanding of things. So obviously, generally, we don't use Golang for this. We generally, if I ask you to make a machine learning model or something, 9 times out of 10 you will go to Python. And that's probably because it's the right thing to do. But again, we can also use Golang, we can also use Ruby, and we can also use other languages for visualizations and making small plots, or even just doing simple tasks for your college or school work. So you can try out these libraries, and you can look at this other perspective of Golang. So overall, thank you so much.
Okay, let's give another round of applause to our speaker. Come on. Okay, so now is the time for questions, and today we have some special prizes for the best question, and our speaker will decide who will get some T-shirt. So it's I think it's quite a nice prize for good questions. So please, you're welcome. Raise your hands, and I'll get you the micro.
Honestly, I had to speed it up so much. You're very welcome to ask any questions. I'd be happy to answer. Yeah. Yeah, go ahead, sir.
Yes, thank you for nice presentation.
Okay.
When I have similar problems, when I need to visualize something, I usually use JavaScript and make an API to Go. I just ask, why did you decided to do it like in Go directly without this? Maybe simpler to make calculations in Go so they are visible, and to make the diagrams and other things in some different software. Why you decided
so
to
it's
do
actually
like
not
this?
in pure Go. It's actually not.
Okay,
in pure Go.
okay.
It's not. That's a decent question, but no, it's this is actually using GNU plot. So it's called plot because it uses GNU plot with Golang. It's actually a scripty thing put together. It's not for pure Go. I'm not that smart. Come on.
Oh, okay. So I just want. How did you do this graphing with Go?
Which one? Which one? This
No,
one?
no. I just wanted to.
This one?
Yeah.
Okay, so basically what is happening is like, well, let me go here. Oh, wait, shit. Yeah. So basically what's happening here is if you look at the code, you basically have, you're trying to calculate the value of a slope of a line and the intercept of a line. Mx, the equation of line is like y equals mx plus c. So you calculate m and c of a line using gradient descent, which, and the math for that, oh shit, not my emails. So the math for that is, it's pretty simple. If you search for like gradient descent, you will find like this is all the math for gradient descent, like how m and c are calculated for the slope of line. So every time you go through these different iterations of the algorithm, what happens is like the algorithm improves upon its previous solution. It comes down and downwards down the slope. So you look at this. So initially, let's say the algorithm says that you're at this top place, and then it slowly goes downwards. So it's improving upon the solution. So when you actually try to see it in sort of wait. When you actually try to see it in sort of a visual fashion, you see that the slope is actually changing. So after every 100 iterations, I'm trying to print the current scenario of what the line is.
Thank you.
All right.
Hello, thank you for presentation.
All right.
Yeah, I wanted to ask how do you propose to visualize not just data, but I mean in teaching way. I mean you propose to visualize graphs, heaps, some other computer algorithms. So what examples of other visualizations for studying do you have here?
You mean other than algorithms itself?
Yeah, what is the best solution? I mean, what is the best example of some computer algorithms that you visualized?
Oh, well, okay. So, okay. You know what? Let me show you something. So basically, this website, Visual Algo. So Belarus, guys from Homel have a very nice algorithms community. I guess you guys are really strong on code forces. If some of you are, please talk to me. I'll be happy to talk to you. So there, these algorithms and these this is a website that visualizes all these generic algorithms that you want. And I don't know how it was written, but it does, it does visualizations for like union find, for for all Fenwick tree, segment tree, and all these visualizations really help. The problem with this website is that you can sort of theoretically understand the algorithm, but that doesn't mean you get to see the implementation. If you use my library, you get to see the implementation besides the theoretical understanding of the. So I mean, yeah, pretty much every graph algorithm can be visualized. You take Dijkstra or Bellman-Ford, whatever. Well, not Bellman-Ford, but whatever.
Any more questions? Nope. Okay, Arafat. So we need to decide between the two. The first question?
Yeah.
Okay.